right, so if we have this problem, if we have the vanishing gradient problem with all squashing activation functions, then one way to, if not solve, at least manage it is, let's just not use a non-squashing activation function, right? So it was long thought that activation functions needed to have certain properties being bounded among them. And what I mean by bounded is having some upper limit, right? So if you're a function, then by bounded I mean you've got some upper limit, excuse me, that you approach, right, that your value approaches, f approaches whatever your bound is as your input goes to infinity, right? And if you think about it, that kind of means your function has to squash, right? It has to have some kind of structure like this, right? Where it flattens out, and in this flattened area, as you approach your bound, then your gradient is going to be small, right? And it turns out we've since found activation functions that work even though they don't bound, even though they're not upper bounded and don't squash, right? And the first we're going to look at is the rectified linear unit, which I'm going to abbreviate like this. And even if it sounds stupid, so abbreviate it like this, and even if it sounds stupid, I'm going to pronounce it ReLU, just because I don't know what else to call it, and that's fun to say. So the rectified linear unit was introduced in a paper in 2000 in which it was biologically inspired. It was described in terms of modeling populations of spiking neurons in the brain. And the reason that it would do that is because, the reason that it would do that is because populations of neurons basically have a spiking rate that looks like that. So the ReLU looks like this. Populations of neurons in the brain kind of act like this, and that their spiking rate is 0 until their input reaches a threshold, and then if you have a large enough population, the growth is approximately linear. That was basically the argument. So this is the rectified linear unit, right? It is 0, so for any number x, it is 0 or x, whichever is bigger. And what that means is, right, so for the entire positive half, that's x, right? Because x is always greater than 0. So x, if x greater than 0, 0 otherwise. For the negative half, that's 0, right? I may have described that poorly because I probably shouldn't have tried to describe, like, populations of neurons, right? But it's either one of these things equivalently, and if you want to graph it, it looks like this, right? So it's x for x greater than 0, 0 for less than or equal to 0, which is just this kind of, right? It's 0 over here, and then it's just your input x over here. And so what's the derivative of that? Well, the derivative of a component-wise defined function is just the derivative of each of the components in each of those regions, which is to say the derivative of ReLU is 0 when you're less, so it's 0 when you're less than or equal to 0, and 1 when you're greater than 0. So it's this step, right? 0 over here and 1 over here. Real easy, right? Very, very easy functions to write, right? Technically, there is a discontinuity at 0, but there's a bunch of different ways you can remove it. You can just assign it the value 0.5. You can assign it the value 1. You can assign it the value 0. In sort of math terms, you are unlikely enough to ever get your function called on exactly 0 that it kind of doesn't matter, right? So it can just sort of be whatever, right? And the way that I wrote this down, right? 1 if greater than 0, 0 otherwise. The way that I wrote that ReLU prime of 0 would be 0, right? Because it wouldn't be this. 0 is not greater than 0, so it's that. Oh, right, and note, right, so tan h was this kind of S-shaped thing that went between -1 and 1, right? So all of our outputs for tanh had to be in the range -1 to 1. Well, ReLU runs from 0 to positive infinity, right? So our ReLU units can output any positive number, right? So for ReLUs, right? So, and remember that your D, right? Your desired behavior has to be in the range of output of your function. So for ReLUs, we can use for our D, for our labels, right? Any value from 0 to positive infinity, right? If we used 1 with tanh, that was bad, because we'd be causing it to saturate. We can use 1 with ReLU. We can use 500 with ReLU, right? There are reasons we probably shouldn't, but in principle we could, right? But with tanh, we could use also -0.5, and we can't with ReLU. With ReLU, the lowest value a ReLU unit can ever produce, ever, is 0, right? So our desired behavior, our D, our labels, have to run from 0 to any positive number, but probably still 1. So remember that graph before about the error signal as the input goes up? Well, it turns out that's just this, right? Because remember, that's D equals 0, right? So that's, okay, let me start over again, right? So we're graphing 1 minus D minus f of x times f, I did it wrong again, y. 1 minus f of y times f prime of y. Well, so we're using 0 as our target still. F prime of y is just y. I'm sorry, okay. F of y is just y for all positive numbers, right? Because that's ReLU, right? ReLU of any positive number is that number. So f of y, for any positive number is just y. And derivative of ReLU of any positive number is 1. So there we go, right? Our error signal with ReLU, at least in the positive half, is just negative y times 1, which is just y. So it doesn't vanish. That's the point, right? As the error goes up, the error signal goes up, it does not vanish, and we don't have the vanishing gradient problem, at least in the positive half. So the right half is great. But what about the left half, right? The less than 0 half. Over here we have a problem, right? Because over here we see that for all of negative infinity, right, from 0 to negative infinity, our error signal is 0. Whoops. So now our network doesn't saturate in the positive half, but what if we get a lot of negative activations? Well, now that's kind of bad, right? Because again, we have to find D minus f of y times f prime of y, right? And if if y is negative, right, then that's D minus 0, right? Because ReLU of any negative number is 0, times 0, right? Because ReLU prime of any negative number is also 0. So for the negative half, our error signal is zeroed out completely. It's not even tiny, right? It's not even close to 0, it's just 0. If our network produces a lot of negative values, then it can never learn because the error signal keeps getting zeroed, and so the weights never get updated. This can actually be a problem. If we have a unit, a ReLU unit, that gets stuck, so it's consistently producing a lot of negative values, then it never learns, and it just stays there where it's always producing a 0 output, right? So the weights are adjusted so that y is always 0. The weights are adjusted so that y is always negative. The ReLU is always producing 0. It never gets any learning signal, right? Because it would have to have a non-zero output to learn, and it just gets stuck. This is called the Dying ReLU problem. All right? Fun quick fact, the 2000 paper that introduced these things noticed that many of them were zero, right? That at any given time, if you had a bunch of ReLU units, a lot of them were going to have zero output. They thought this was a sign of sparsity, which was good, because the brain is kind of like this. The brain, or in the brain, often only neurons that represent an active functional computation are firing, right? The activations of the neurons in your brain are sparse. And so the kind of neuroscience-y people who were introducing the ReLU thought that was a good thing. I actually don't know if there are papers on this, but I kind of wondered if they were already seeing the Dying ReLU problem and not realizing it. Because from our perspective, building a neural network, units that are stuck permanently off are not doing work. We can come back to that. I have heard it said in informal conversation that ReLU networks have slightly lower learning capacity than tanh networks for the same depth, because the ReLU is a little less nonlinear. I do not know if that is true, and more to the point, I don't know if it matters, because a ReLU network is going to be much deeper than a tanh one, and the rapidly expanding depth will almost certainly overwhelm any sort of loss in learning capacity, right? So it's worth mentioning, but we can just sort of gloss over that, right? So ReLU make your network so much deeper that it doesn't matter. So the solution to the Dying ReLU problem is the Leaky ReLU. So instead of 0 for the negative half, we use that shouldn't be negative. We use alpha x, where alpha is some very small constant, right? So let's call it 0.1 or so, right? So now our network is x, right, if x is greater than 0, or 0.1x if x is less than 0. And the derivative of this thing is now 1 if x is greater than 0, or alpha, and again, we can say like 0.1 if we're less than 0. Now our error signal is never multiplied by less than alpha, right? If our problem is that derivative going to 0, right? LRELU prime is either 1 or alpha, right? Read -1. Right, so again, this never goes completely to 0, right? It's either 1 or -1 at the smallest. So now our gradient doesn't vanish. So now we should get error signal even when we have negative activation, right? So if we graph it, it just looks like this. So instead of being like a sort of, I don't know what to call it, like hard angle, you have this kind of change in slope, right? Where it's shallow and steep. LRELU, so unlike ReLU, LRELU can produce negative values, right? This thing technically runs from -infinity to infinity. But a negative output is going to involve exploding weights, right? Because you're multiplying by this tiny number. So you should probably still, in general, restrict your desired outputs, your labels, to 0 to positive infinity, or more realistically, 0 to 1. Right? So even though this thing can go negative, we still want to keep the desired output in the range 0 to 1. And then the gradient just looks like this, where, right, if this were the ReLU, we would have 0.0 down here. But now instead it is like 0.2 to 1. And for these slides, yeah, I was using alpha of 0.2. Whoops. Right? So now if we graph our error signal, we basically see, right, it's still less, but it's not 0, right? That's the important bit, right? So again, if the target output was 0, what does the error signal do, right? Well, as we go positive, it increases dramatically. As we go negative, it increases slowly, or Yeah, so the absolute value of it, right? The degree of error increases slowly. But it's still increasing, right? The error signal is getting stronger the wronger we get, and so we are still going to learn. Okay? So that leak factor alpha is important, right? With very large alpha, you get better error backflow, but you also lose some nonlinearity, right? So, excuse me. As alpha goes up, you are going to get, in theory, better error backflow, but you'll also be approaching not having a nonlinearity, right? You'll lose computing power, and you also potentially will trade off stability, right? Because as it turns out, the network being able to saturate is actually kind of important for it being able to settle down into a stable behavior regime, right? So small alpha is going to get you better stability and maybe better learning capacity, question mark? Whereas large alpha is going to get you better error backflow, right? In practice, values between 0.1 and 0.2 are probably good, right? I think TensorFlow's default is 0.3. I don't know how they picked that. Maybe they have good reasoning behind it. I would prefer to, I think, yeah. I would prefer to be a little bit lower so that we're a little bit closer to that ideal ReLU. Oh, we will have a code demonstration later. So this is the time when I would usually go, let's go to the code. I'm not going to do that right now because what we're going to find out is there's actually not a lot of code to go to. Basically, when we're done with this conversation, we're just going to end up changing a line. So we'll see all of the code at once, right?